Okay, so we're taking a look at the error in using Euler's method. And so I just need to set up a little bit of notation. Um, First off, I'm going to let y1 be the computed value of our approximate solution. Okay, using the Euler's method after one time step. And then I'm going to let y of t, right, be the actual solution. Okay, so then for example, we know that y1 is y0 plus h times f of tn yn, right? By the way, where did the f come from? That is our differential equation, right? Okay, and so if I take a look at y of t, I can write the Taylor series for y of t, and in fact I'm going to shift from t0 to t0 plus h. Right, now this is the actual function, right? So I start at y of t0 plus y prime of t0 times h, or I'll put the h in the front, I guess, and then plus h over 2 h squared times y double prime of t0 plus big O of h cubed. Now when we write this notation, right, that means that the rest of the terms here involve h cubed or higher as their okay. Yeah, the rest of the terms are h cubed and higher. Okay, now this y prime here is actually this, right? And so I could rewrite that as y of t0, or maybe I'll just write it as y sub 0, because those are the same, right? There's no error at time step 0, plus h times y prime at t0, which is f of t0 y0, okay, plus h squared over 2 y double prime of t0 plus big O h cubed. Okay. This looks interesting here. Well, it will look interesting here if I made a correction. There we go. Now it's the exact same. Yeah, this is supposed to be y1. Okay, so now I know the difference between the computed value at my first time step minus the estimated value is equal to h squared over 2 times y double prime at t naught plus some other terms. Now, getting a handle on this stuff is what might be a problem, right? But there is another way of writing the Taylor expansion, and the other way of writing the Taylor expansion is, instead of writing this last term here, you can actually write this using an error term. And the way to do that, so let me make a star here. Alternative form is to write y of t0 plus h equals y of t0 plus h times y prime of t0 plus, make sure I'm using my notation correctly, h squared over 2 y double prime at c. Okay, and this is going to work if y has a continuous second derivative. Okay, so I'm assuming that y has a continuous second derivative, and this c here is in the interval from t0 to t0 plus h. So often people will just say, well, um, suppose that suppose that the second derivative is bounded by some constant m. Then this is even easier to write. We can write y of t0 plus h. In fact, maybe I'll go ahead and make this my y1 again and bring it over to the other side. So that's y1 is equal to, well, now it's less than or equal to h squared over 2 times m. Okay, and so now we have a really good upper bound on our error, right? And so we would say that the local truncation error here, that's what we're computing, the local truncation error is on the order of h squared. Okay, that means it's approximately proportional. We could say approximately proportional to h squared. That would be another way of saying the same thing. Okay, and then there is a way of looking at the global truncation error, but there's some messing around we need to do. I didn't want to introduce new topics right now at this stage, so we're just going to say that the global, it can be shown. It's not really hard to show, it just takes a little bit of time to show. It can be shown that the global truncation error is on the order of, well, maybe say is proportional to h. Okay, and so this is definitely saying, right, if you want better approximations to your solution, then h needs to drop to 0, and the error will drop in proportion to h. Okay, but this is saying that the truncation error will drop by h squared, right, instead of just h. Good. All right. And so I believe all the other Euler formulas, well, the backwards Euler is also order h. I wanted to mention the next algorithm because that's actually an order 4 algorithm, and it's kind of the workhorse of the DE solvers, and that is the Runge-Kutta method. Or algorithm, the Runge-Kutta algorithm. Okay, and so the idea behind Runge-Kutta is that we're actually going to be taking several sample steps here. We're going to take our sample at time tn like we normally do, but then instead of going directly up to tn plus 1 like we did in the improved Euler, we're actually going to also take a look at what happens halfway in between. So that would be tn plus h over 2. And in fact, the fourth order algorithm will actually take two sample slopes here, and it's going to take one sample slope here and one sample slope here, and then we're going to try to take a weighted average of those four slopes. Okay, so again, this is going to, so we're going to try to approximate our solution at 4 different points. Okay, let's see, I've got 1 minute to go on that, so maybe I'll go ahead and stop here, and we'll actually we'll continue and write down the actual method in the next video. See you then.